Dr. Shweta Sharma from ABES Engineering College, Ghaziabad. In this lecture, I'll be discussing about atropisomerism, chiral drugs, and geometrical isomerism. The content I will cover in the lecture is atropisomerism with examples, chiral drugs with examples, geometrical isomerism phenomena, cis-trans nomenclature, and EZ nomenclature. Atropisomerism is the phenomena which arises due to the restricted rotation around a carbon-carbon bond, and it results in optical activity without chirality. So what is the basic feature, or what is the necessary condition for optical activities now is the asymmetry in the molecule and not the chirality in the molecule. So atropisomerism is the optical activity in the molecule without chirality. Biphenyls is the class of compounds which exhibit this phenomena. For example, this biphenyl, which has two bulky group at the ortho position, show the atropisomerism phenomena, which is optical activity without chirality. Two bulky groups on the molecule, carboxylic group and the nitro group at the ortho positions. This is the nitro group. These two presence of ortho group at the bulky group at the ortho positions prevent this single bond to rotate. Now, this single bond has restricted rotation, and the one planar benzene ring is perpendicular to the another benzene ring. This molecule has asymmetry, completely asymmetry, and it show atropisomerism phenomena, which means optical activity without chirality. This molecule has no chiral center, but still it is an optically active molecule due to the asymmetry in the molecule, which arises due to the restricted rotation in the biphenyls due to the presence of bulky group at the ortho positions. If I'll draw the mirror image of this compound, this mirror image is the non-superimposable over each other, and these enantiomers are known as optical atropisomers. These optically active enantiomers are known as atropisomers. This is the mirror image of this compound, and these two isomers, which are enantiomers or non-superimposable mirror image of each other, are known as atropisomers. Another class of compounds which show this phenomena are the allenes. Allenes are the cumulated dienes. Cumulated dienes means which have the double bond continuously like this. This allene has two carbon bonds, double bonds, which are perpendicular to each other. This is the structure of the molecule which show this atropisomerism phenomena. The plane of this carbon double bond is perpendicular to the first double bond. Therefore, these two substituents, methyl and hydrogen, are shown as above and below the plane, whereas the substituents on the first carbon atom is shown in the plane. The mirror image of this molecule is non-superimposable over each other. This class of compound or this molecule also show atropisomerism phenomena or optical activity without chirality. In this molecule, there is no chiral center, but this molecule is optically active due to asymmetry in the molecule. These isomers are known as atropisomers, or these enantiomers are known as atropisomers, and this phenomena or this happens due to the complete asymmetry in the molecule. So, asymmetry is the necessary condition to show the optical activity phenomena, not the chirality. Spirines. Spirines also show this phenomena. Spirines are the cyclic compound which have carbon atom common in them. They are the bicyclic compounds having one carbon common in them. One carbon common in them. For example, this system is a spirene, and this carbon is common to both the rings. This molecule show optical activity phenomena the mirror image of this compound is optically active. Another example is this ring having one carbon common in this. This is the common carbon. This molecule also show optical activity phenomena without chirality because molecule has complete asymmetry. The mirror image of this molecule show optical activity, and these two enantiomers are optical isomers, or they are atropisomers. These two are atropisomers. Next is the chiral drugs. Chiral stereocenters show different chemical properties against chiral centers. Chiral stereocenters are very specific and they show a very specific reaction when the another reagent is also chiral in nature. If any drug is chiral in nature, then its different enantiomers will show different pharmacological activity in the body because the biological system responds differently against the different optically active enantiomers or optically active molecules. Therefore, if a chiral drug for both the enantiomers of the chiral drug do not show the same pharmacological activity in the human body. For example, this is the thalidomide. Thalidomide exists in both in a two enantiomeric forms. This is the S enantiomer of thalidomide or S form, and this is the R enantiomer of the thalidomide. Thalidomide is used as a sedative. It is a very effective sedative with a soothing effect that relieves the anxiety and cause drowsiness in the patient. So it is used as a soothing effect to treat the patients, whereas the S enantiomer is not a drug. It is not used as a medicine, and it causes a teratogenic birth defects when that is a child is born with a deformed body parts if this drug is taken as the racemic mixture form. So this enantiomer has a S enantiomer has a adverse effect on the human body, whereas R enantiomer is used as a effective sedative for the human body. So in this way, we can see that how the chiral structures or chiral molecules are extremely specific in their reaction or chemical reaction when they are used as a drug in the human body. Another example is a carbone. Carbone, R enantiomer of a carbone is used as an air freshening product and it is used in aromatherapy. This is the R carbone. It has a very different fragrance, R carbone, whereas the S carbone show a suppressant effect against the high fat diet. In this way, these two enantiomers of carbone, both R and S, have different effects again on the human body. The R carbone smell like a spearmint oil, It is a smell like spearmint essential oil, whereas the S enantiomer smell like caraway oil. These two are essential oil. So these two isomers smell differently. R enantiomer give the smell of spearmint oil. S enantiomer give caraway oil. Also, their action is again extremely different when they are used in the human body. R enantiomer has a freshening effect and are used in aromatherapy, whereas S carbone is used as a suppressant effect against the high fat diet. Next is the ibuprofen. Ibuprofen is a very common painkiller which is used as a trade name by the Brufen. The S enantiomer of ibuprofen is an effective painkiller, whereas R enantiomer has no pharmacological effect on the human body. R enantiomer is not has no effect on the human body, neither negative effect or any positive effect, whereas the S enantiomer is used as an effective painkiller on the human body. Geometrical isomerism. This isomerism refers to the compounds that contain the same empirical formula but different in the structural arrangement of atoms in a space. Generally, geometrical isomer arises when the carbon-carbon double bond shows the restricted rotation and the atoms or groups that are bonded to the doubly bonded carbon do not change their positions in space, and their structural arrangement become fixed due to the presence of carbon-carbon double bond which do not rotate or show restricted rotation. When the similar groups present on the carbon-carbon double bond are on the adjacent position, then it is known as the cis isomer. And when the similar groups are present on the opposite position around the carbon-carbon double bond, then it is prefixed as a trans isomer. For example, this molecule is a cis isomer. Both methyl present on the adjacent position on the carbon-carbon double bond, and both hydrogens, which are similar, present on the same side of the carbon double bond. This is a cis isomer. Trans isomer, when the methyl groups are opposite, similarly when the hydrogens are opposite. This is a trans isomer when similar types of groups are opposite to each other around the carbon-carbon double bond. This is geometrical isomerism or cis-trans isomerism. Next is the EZ nomenclature. In geometrical isomerism, EZ nomenclature is more practiced because when the groups around the carbon-carbon double bond are different, then in that case, it is not possible to assign cis or trans structures to those groups. In this case, when the groups around the carbon double bond are different, Kahn, Ingold, and Prelog priority rules are followed, which are commonly known as CIP rules. This CIP rule says that when the different groups are present around the carbon double bond, the priority is given to all the four groups on the basis of the atomic number. And now, on the basis of priority, E and Z is a form is assigned to them, where E isomer stands for the German term antigen, which means opposite, and Z isomer is assigned to that molecule in which similar priority groups are present on the same side of the carbon double bond, where Z form is taken from the German word zusammen, which means together. For example, this molecule has four different groups, or this is the presence. This is the molecule having different groups. Now, in this situation, both the groups present on the first carbon atom, doubly bonded, is assigned the priority on the basis of atomic number. This methyl group has high priority. It is assigned as 1 as compared to the hydrogen, which is assigned priority 2. Similarly, now assign the priority to both the groups present on the second carbon atom. Second carbon atom has assigned the priority in which bromine is 1 because it has higher atomic number as compared to the methyl group. Methyl group has second priority. Now we can see that both the high priority groups are present on the same side of the double bond, and both the lower priority group are present on the same side of the double bond. In this case, this is a together, this is a Z form or Z form. And if I'll draw the E structure of this molecule, this is the E form. 1 assigned priority, this is the priority number 2, methyl priority 1. Bromine assigned priority 1 and methyl is assigned priority 2 on the basis of atomic number. Now we can see that both the high priority group are opposite to each other and lower priority group are now opposite to each other. In this case, this is E form. In this way, we can assign the different priorities and structures to the isomers which have different set of groups around the carbon-carbon double bond. Another example we can take, this is the molecule. We can now assign the priority on the basis of atomic number. Methyl is 1, hydrogen 2. Ethyl 1, hydrogen is 2. In this case, both high priority group are on the opposite sides and lower priority group are opposite to each other. Therefore, this is a E form or E isomer. And the Z isomer of this molecule is when both the similar type of group or high priority groups are on the same side and when both the lower priority groups on the same side. This is the Z form of the molecule or Z isomer. In this way, we can assign the E and Z nomenclature to the molecules which have different groups or atoms present around the doubly bonded carbon atom. These are the references. Thank you all of you.